the name of God, today we're going to address molecular effusion based on the kinetic theory of gas. Before I continue, I make some recap of what we have done so far, calling it ABCD, and hopefully it's going to flow that easy. We started with Maxwell-Boltzmann distribution. From there we computed the probability for a molecule within a container of gas to have velocity in an infinitesimal range from v to v plus dv. So that probability we have discussed, it's going to be f of v times dv. So f of v is the probability density function, the Maxwell Boltzmann density function, right? That was point A. The next point I think we have derived is like the number of molecules kind of this is per unit volume. So in A we were talking about a single molecule. Here in B it's a number of molecules having their speed in the range from V up to V plus dV, okay? And that number per volume is going to be m. M is the number density, is the total number of gas molecules divided by the total volume times f of v dv. This kind of one can think of f of v times dv to be the fraction of molecules having speed within the range v and v plus dv. So if you have the fraction of molecules and you multiply that with the total number of molecules, then you get what you want. Given that little n is the total number of molecules, capital N divided by big V, which is the volume of the container. Right. And the next point we have addressed was called point C. So still we want sort of the fraction of molecules moving within a range of angle within an angular range. So kind of a fraction of molecules, right, having speed. So I'm going to use a shorthand such that the speed is within this interval of v and v plus dv. V plus dv. So they have a speed like that. On top of that, we want those molecules to be moving relative to some chosen direction. So they're moving in such a way that the angles which the molecules velocity sustain lies within the range of theta and theta plus d theta. Right, so this is another range. So the fraction of molecules moving with velocity between v and dv, and also moving within direction of theta and theta plus d theta, is what we actually want to find. And that number, if it is fraction of molecules per volume, with this property, actually it's going to be point D, okay, which is like what we have, the answer in point B, number of molecules per unit volume, right? It is N F of V dV, right? Times fraction times fraction of molecules moving with directions in this interval of theta to theta plus the theta, right? And this fraction of molecules with this property that they are moving relative to some specific direction within angles theta up to theta plus d theta, we have found that to be 1/2 sine theta d theta. So actually this is point C. Let me sort of underline it here. This is point C. Right? So simply we want the fraction of molecules out of all the molecules within a container of a gas. We want to select those ones that are traveling at an angle, let's say theta. So this is V, it is vector. This is some reference direction, right? So we want molecules moving between from here to here is theta, up to from here to here it's going to be theta plus d theta. So there is an kind of a window of direction, okay? So that fraction we have shown that it's going to be equal to 1/2 sine theta d theta, right? So combining the two, that is the points in B and C gives D for us. So if I write kind of B combined with C, it gives us point D, and point D, I'm going to write it again, is going to be N F of V dV 1/2 sine theta d theta. So this is the number of molecules per unit volume moving with speed between V and V plus dV, and moving with direction within theta and theta plus d theta. Okay. Point E, we go to the next page. I think it's better. For point E, actually we want the number of molecules. Okay. As in point D, that will hit a wall of area big A within a time interval dt, right? So if we want number of molecules, one can imagine we can get that from sort of number of molecules per unit volume times some sort of volume quantity, a measure of volume, right? So now we want, there is a wall, let's say, that has a width A, and we want molecules that comes and hit this wall, the number of molecules hitting the wall within a time interval dt, right? So this volume we compute it as kind of the volume in which molecules are going to sweep before they hit a wall within a time dt, right? That volume we computed to be a sort of a v cos theta d theta. So it's like area times length. The length traveled is v cos theta dt, right? So we're going to multiply this volume with the answer we have obtained in point D, which is the number of molecules per unit volume with speed between v and v plus dv and direction within theta and theta plus d theta. So this is n f of v dv times 1 over 2 sine theta d theta, right? So that's it for the point E. We moved on to compute flux from that. So moving to point F, define molecular flux sort of as number of number of molecules per area, so number of molecules hitting a given area per time. With this one can see that we have an elemental flux of molecules. We call that elemental flux of molecules d phi. So phi is going to be the molecular flux, d phi is going to be the answer we have derived in point E, which is kind of a v cos theta dt as the volume times the number per unit volume, and f of v dv 1 over 2 sine theta d theta. So we're going to divide this by the area of the wall under consideration and the time interval dt. Okay? So this is going to be, after doing the cancellations, going to be v cos theta n of v dv 1 over 2 sine theta d theta, right? And then one can integrate all of these d phi over d theta and dv. From there we're going to compute the molecular flux phi. We have seen that this is 1 over 4 number density times the average speed of the molecules, right? From this we moved on to point G. Point G, we were trying to compute the pressure, gas pressure. We started by considering a single molecule. So let's say there is an elemental pressure element due to the interaction of a single molecule with a wall of the container of a gas. So if we call that dp molecule, so here we're talking about a single molecule, and remembering that definition of pressure is sort of force exerted on the area divided by the area. So, and one can write this as F dt divided by A dt, because we're trying to compute sort of the force exerted upon the wall of the container within a time interval dt by a single molecule. So F times dt is kind of a change in momentum. Remember, F is m dv by dt, so I can write, if m is constant, I can write force as change in momentum with respect to time, right? Or F times dt is going to be some sort of a change in momentum divided by a dt. So this change in momentum happens because the molecule comes with a specific velocity. It hits the wall, and we assume that it bounces back without losing energy. So we have discussed that in previous sessions. Delta momentum is going to be 2m v cos theta. So divided by, this is d a dt, right? From this we can compute the elemental pressure due to number of molecules. This time around we're not talking about one molecule, we're talking about molecules, number of molecules, right? So we can get this to be the P due to a single molecule times what we have derived earlier in this is going to be like number of molecules that will hit a wall with area A within time dt. These molecules, remember, have a speed between v and v plus dv, and direction between theta and theta plus d theta. We have computed such number of molecules as a v cos theta dt, and f of v dv times 1 over 2 sine theta d theta. So if you do substitution, we know what the P from a single molecule is, and if we integrate over the theta and dv, the A and dt are going to cancel. We're going to obtain an expression for pressure, which we have done. We have seen it is 1 over 3 mn times average of velocity squared, or one can write it as n kbt using the expression for the average velocity squared, which we have derived earlier, right? And this can be written in several forms as PV is equal to n kbt, or PV is equal to n mRT. So n m is number of moles, number of gas molecules divided by Avogadro's number, and so on and so forth. So this is up to kind of point G. Point H is the next subject, which we're going to address today. Now, point H. Again, we're going to talk about molecular effusion. So this is sort of if you have a small hole on the container of a gas, naturally the gas molecules are going to come out. So the gas escape via a small hole is called molecular effusion. So this is gas escape out of container via a small hole. Okay. And this is another form of flux, one can like think of it that way, because we are considering some area which is attributed to the hole in the container. So we want the number of molecules going out or crossing out of that hole per unit time. So naturally we go straight to the formula for flux, which is 1/4. We have derived that to be 1/4 n average of speed. Right, substituting this is the same as 1/4 p divided by kbt times square root of 8 kbt divided by pi m. So this is average velocity, and from this formula, which is kind of p is equal to n kbt, we can write n to be p divided by kbt, right? So making the substitutions, one can get an expression for the flux in terms of pressure and temperature of the gas. Okay, so this is p divided by 2 pi m kbt square root. Okay, so one can see that okay, flux is directly proportional to pressure if temperature is constant, and also flux is directly proportional to the inverse of square root of m if we keep other things constant. So keeping pressure and temperature constant, we can see that flux is directly proportional to 1 square root of m. Okay? This is an important and interesting relationship, that kind of the number of molecules getting out of a hole really depends on the mass. So one can use that to do some kind of physics, to do some phenomenology. For example, if you have a container which is having different types of molecules with different mass, you can use this property that the flux, the effusion of gas out of, let's say, a small hole in a container depends on the mass. Since it depends on the mass, then the gas is coming out of the container, they're going to come out at a different rate. Some will come faster than the others, right? So the lighter ones would come out faster. So you can use this to kind of separate mass. So if you have gas, a mixture of gases of let's say two different types of molecules, you can use this to separate them. So if it is difficult to separate using chemically, you can use this molecular effusion. So lighter gas molecules will effuse faster. Let's write that. Lighter gas molecules will effuse faster than heavier ones, right? Therefore, you can use this concept, use this property for mass separation. Yeah. So this is important again for scenarios where mass separation, let's say, is difficult or not possible to be done chemically. An example is, let's have two examples. Helium gas will effuse out of a small hole sorry, let me pick a pencil. Out of a small hole much faster than, say, nitrogen gas, nitrogen molecules, right? How much faster? By a factor. So you can use the inversely proportionality kind of relation. So mass of the nitrogen molecule divided by mass of helium. We take the square root. This is about this is 28 divided by 4, about 2.6 faster. So this is one example. One point about what small means. I think it's relative to the sorry, let me take this. Relative to the let's say mean free path. So mean free path is something we're going to address a little bit later, right? So I just want to say that small is relative to something which you can actually calculate or sort of measure. Another example, number 2, is one can use this concept to kind of separate uranium. So if you have uranium fluoride, UF6, this is uranium 238. So you just need the mass of that divided by mass of uranium 235. Okay. For producing like uranium to be used, let's say, in reactors for generating electricity, you have a gas, a mixture of two gases, uranium fluoride containing two versions of uranium, and one can use molecular effusion to kind of separate them. So this mass is 352.0412, let's say, according to the book. We're not going into details how that is determined. There is this course about nuclear and particle physics. If you attend that, you can have details of how this mass can be computed. Yeah. So square root of this is approximately 1.006. So it's a very small factor, but good enough to do the job for mass separation. And from effusion, one can compute like effusion rate. Sorry, effusion rate is going to be number of molecules per time, so we multiply the flux by area of the hole, this kind of molecule escape rate, and one can use this somehow to measure the pressure of gas, or the pressure of a vapor, of a gas vapor. There is an experiment for doing this, right? Knowing the expression for the flux phi, we know what it is. It is so P divided by square root of 2 pi m kBT, square root of that. Right, so this is the flux, and we're going to multiply that with area. Okay. Experiment called nesting. Used for nesting method for measuring the pressure of gas vapor. You can measure pressure of gas vapor this way. How does it go? We need first to have a container with the vapor. So there is gas vapor somewhere here, and there is a liquid from which the gas vapor is being produced, and then we want to construct a little hole here such that the gas vapor molecules effuse out of the hole. Right? So all this container, let's say, is put on top of a scale to measure mass somehow. So you have, this is a rough sketch one can play with in the laboratory. So let's say this is a scale somehow, it's measuring mass, right, in kg or whatever unit that may be, just schematic to show what's happening, right? So what's going on is that as the gas vapor molecules effuse out, the mass of the whole thing here is going to change with time, right? And one can compute sort of, let me go back to this color, the rate of change of mass, let's say dm by dt. Okay, this is going to be mass of the gas vapor molecules times the effusion rate, right? So effusion rate is the flux times area of the little small hole. The rate is going to be number of molecules crossing out per time, and if we multiply that with mass, it's going to give us the rate of change of mass of the gas vapor. Okay, and dm by dt, we're going to make it negative because the mass is going to decrease with time. Okay, so this is going to be equal to dm by dt is minus m phi times a. Okay, but already we know what phi times a is, and from there we can kind of see that m multiplying by m phi a is going to be equal to m pa divided by square root of 2 pi m kBT, right? and from here one can compute the pressure to be equal to 2 pi kBT divided by n. This is square root times 1 over n times absolute value of dm by dt. You can do the algebra, and from here using, let's say, using 1 and 2, we can get this, right? And dm by dt, one can measure using this cartoonic, one can measure in the laboratory somehow the rate of change of mass, right? And one knows the area of the little hole, right? One knows the mass of the gas vapor molecules, and also the temperature at which the experiment is being taken. So the right hand side of this equation can be measured in the laboratory, so we can compute the pressure, right? So this is another application of gas molecular effusion, right? So this is point H. Point H, we have talked about molecular effusion. We're going to the next point, which is going to be about mean free path of gas molecules. Mean free path, right? So gas molecules moving randomly within a container are going to have some average of distance they travel before colliding with one another, right? So that is mean free path. And from that, there is going to be something again in which we're going to make use of. It is called collision cross-section. So let's discuss about these two things, beginning with the first one, mean free path. If you recall that the root mean square velocity, it's going to be square root of the average of the speed squared. We have computed this previously to be square root of 3 kBT divided by m, so square root of everything here. What does this mean actually? If one consider, let's say, a non-molecule, let's say oxygen or nitrogen, so the mass is known, and one considers such a gas of oxygen at room temperature. So at room temperature, T is also known. You can compute this to see that it's going to be approximately equal to a huge thing relative to the speeds we're kind of used to. So this is about 500 meters per second for nitrogen or oxygen molecule, right? And instead of oxygen or nitrogen, one can consider, let's say, the molecules in a perfume, right? If I spray a perfume at one corner of a room, if the velocity or if the speed of the molecules is of this magnitude, let's say is 500 meters per second, then it is expected that the perfume is going to be realized, or is going to be sensed kind of instantaneously, immediately, at all other parts of the room. So let's sketch this to have a cartoon, to see a picture. Supposing like some gas molecules, so perfume is released here at one corner of the room. If the speed is like 500 meters per second, then we going to expect that another person sitting at the opposite side would kind of smell the perfume already, kind of immediately. But we know that this doesn't happen. This doesn't happen. The reason is that the molecules of the perfume collide with one another, right? So they may have a speed of with this magnitude, which is huge, 500 meters per second, but they are not free. It's not like releasing like a particle with this speed to freely kind of move. It kind of encounters other molecules along its way. They collide with each other, and that prevents the molecule to kind of reach the other corner of the room instantaneously, right? So how do we measure this? A way to quantify this is if we can compute the mean free path. We can see that mean free path is actually something small, right? So if the mean free path is really huge, is really big, then the perfume is going to be kind of realized, or is going to be sensed immediately without any delay in time. It doesn't happen because there are collisions, and the collisions leads to this kind of a feature that the molecules have a mean free path, an average free path, an average length they kind of cover without colliding with another molecule. So mean free path is important, and it is directly related to collision. So molecules collide with each other, and we're going to talk about cross-section after addressing the mean free path. Okay. So in order to compute the mean free path, we need to kind of address two things. Let's say mean collision time is going to be important. Mean collision time. And this is kind of average time between collisions. Okay. If I know the average time between collisions, if I multiply that with the average speed, then one can compute the average free path for the molecules. So our first target is to be able to compute the mean collision time. Okay. So we begin by addressing collision itself. A simplification is that one can consider two molecules, right? So let's say there is a molecule A, let's say this molecule A is moving with some speed v, and then there is another molecule B, okay, A simplification we can make is that we can assume that molecule V is not moving, so speed is 0, so it's kind of just sitting, right? So collision happens when molecule A approaches molecule B, or when molecule A hits molecule B, right? And the cross-sectional area, so let sigma be the cross-sectional area of molecule A. Okay? The cross-sectional area of molecule A is important. So also the cross-sectional area of molecule B, right? Because one can imagine ordinarily that let's say the bigger these molecules are, the more likely it is that molecule A is going to collide with molecule B, right? Okay, we know that it also depends on the direction. If molecule A is moving opposite to the direction where it can find molecule B, then nothing is going to happen, right? But if we keep direction aside and consider directions of A moving towards B, right? The bigger A is, the more likely there is going to be a collision. The smaller molecules, the size of the molecules are, the less probability we're going to have for the molecules to collide. So this sigma, cross-sectional area, hand wavy, one can think of it as a sort of a measure of how likely or how often molecule A is going to collide with molecule B, right? And we're going to address this more, but for now we want to compute something called mean collision time, because that will lead us to be able to compute the mean free path of the gas molecules. Right? So with the scenario described, let's say within a time interval, dt, the volume which is going to be swept by molecule A, if we call that volume dV, that volume is going to be let's say the cross-sectional area of molecule A. So molecule A have some cross-sectional area. If we assume the molecule is spherical in shape, for example, so that cross-sectional area times the velocity of the molecule times dt is going to be the volume element. Okay, and from there we can compute something. Let us say P1 is the probability of molecule A colliding with another single molecule. So this is a molecule, let's say molecule X, which is any other molecule within the gas, right? In the gas. So this probability is going to be equal to the probability that molecule X or molecule B, as I've stated with this scenario earlier, but it doesn't matter, let's continue with X. Probability of molecule X is within dV, right? So let us read this again. Collision is going to happen, okay, whenever let's say molecule X is found somehow within the volume. So if this is sigma, the cross-sectional area of molecule A, and the volume is going to sweep, it's kind of schematic somehow, it's going to be cylindrical, right? So if for whatever reason molecule X is found within this volume over the time dt, then for sure collision is going to happen, right? Okay. And the probability of molecule X to be within the volume dV, one can imagine, is equal to dV divided by big V. So V is the total volume of the container if our container has a volume V. And if we assume that all molecules in the container are randomly distributed, uniformly distributed, then this makes sense. The probability of molecule X to be within the elemental volume dV is going to be dV divided by V. So this is going to be sigma little v, the speed, times dt, and divided by V. Okay, so this is probability for molecule A to kind of collide with some other molecule X in the container. Next, we can think of P any to be probability of molecule A colliding with any of all the other molecules in the container. So this time around we're not considering just one molecule, we're considering all of them. Okay, Pn is probability of molecule A colliding with any, so you should underline the word any of all the other molecules. All the other molecules in the container. So this is going to be a probability, let's say molecule number 1 is within dV, okay, plus probability of molecule number 2 is within dV, plus all the way, so all of them up to the last molecule, so that would be n. If n is very huge, there is no difference between n and n minus 1. So let's say plus probability of molecule n is within dV. Let me try to write this. Probability of molecule n is within dV, right? Because it's going to be probability of molecule A colliding with molecule 1, or molecule A colliding with molecule 2, or molecule A colliding with molecule 3, or all the way up to molecule A colliding with molecule N. Okay, so and we know what these are. So this is actually an approximation. Alright. So this is approximately equal to that. Again, we assume uniformly and randomly distributed gas molecules within the container. And the approximation is that we are assuming that these events are independent. So the probability that molecule 1 is going to get hit by molecule A is independent of the probability, is independent of molecule 2 getting hit by molecule A, is independent of molecule 3 getting hit by molecule A, and so on up to molecule N getting hit by molecule A. But we know that in reality they are not really independent, right? Because the fact that, let's say, if molecule A hits molecule number 1, then we know that it is not going to hit molecule number 2, number 3, all the other molecules, right? But because the number of molecules are really huge, and we're considering like an ideal gas, and dV is really tiny, then like this approximation can be accepted, right? And each one of those probabilities, we know what they are, therefore we can compute P NE to be equal to the total number of molecules, which is N times P1, which we have computed earlier. So this is going to be N sigma V dt divided by V, and N divided by V is little n, the number density. So we have this nice expression for probability of collision in time. Okay, so this is probability that molecule A will collide in dt. Within time interval dt, there's going to be a collision. Okay. So the next step is we want to compute. Remember what are we doing? We're trying to compute mean free path from the average collision time, right? The next step is we're going to compute, let's say, PT PT is probability of molecule A not colliding with any other molecule up to time t. So we have a molecule A, it's living its life without collision within a time interval t. So time interval t, no collision. Let's say from 0 to t, no collision. So what is this probability? This probability, we call it PT. Okay. From this definition, one can see that the probability of molecule A not colliding within time t plus dt. So the time interval we're now considering is t plus dt, right? Probability, this is going to be probability that molecule A is not colliding within time interval t, and so since we have and, it's going to be probability multiplication and probability that molecule A is not going to collide within the time interval dt. Okay, so this is a property of probability. The same thing, P of t plus dt can be written as, this is P t times 1 minus probability of collision, probability that molecule A is going to collide with something within dt, right? So here is p dt is probability of no collision within time interval dt. This is exactly going to be equal to 1 minus probability of having collision within time dt, right? So this is something which we can accept. So this is pt into 1 minus probability of collision within dt is what we have computed earlier. So this is n sigma v dt, right? So we have this expression to be intact. We can have another expression for probability of molecule A not colliding within time interval t plus dt using calculus. Okay, this is going to be a probability of pt plus some dp if we assume dt to be really small. So this is coming from this rule of calculus, right? And comparing these two, if I call this star, and if we call this star, comparing the two leads to something. So it's the same thing we are computing using two approaches. One approach is P of t plus dt using properties of probability. This has to be the same as pt plus dt using calculus features. Whichever method we choose, it's the same quantity we kind of computing. So this way we're going to have, let's say, pt into 1 minus n sigma v dt is going to be equal to pt plus dp. And from there you can see that some cancellations are going to happen. This is going to cancel the 1 which is here, and you're going to have an expression that 1 over p dp by dt is equal to minus n sigma v. Okay, and this implies that pt is equal to e to power. If you do the integration, you get this using the boundary condition p of 0 to be equal to 1, right? So integrating this differential equation, you're going to get pt, which it really makes sense that the more time it takes, the less this probability is. So this probability goes to 0 as time becomes bigger and bigger, or as time goes to infinity. That time, if you give time, with time, molecule A is definitely going to collide with something. So the probability of molecule A not colliding, if t is really big, is going to be 0. So t big, you have exponential minus t, it's going to tend to 0. And the probability of molecule A not colliding at t0, one can imagine it's 1, right? So the time interval is really small. There's no time interval, so no collision, right? So p0 is equal to 1 is also kind of motivated. You can see one can accept that. So this is a nice expression. It's going to be useful if we're going to use it. The probability that molecule A is not going to collide at all over the time interval t is given by exponential minus number density times the cross section times speed times t. Okay. The next thing we're going to compute is probability of molecule A not colliding up to time t, but then colliding after the next dt. Okay, so if we go to next page, probability, oops, if I pick a different color, probability molecule A not colliding up to time t, and so this is important, and then colliding after the next time interval dt. So let's say this is 0. From time 0 up to t, we want no collision, but then from t to t plus dt, so this is t plus dt, so this interval is dt. We want to have collision here, right? So this is going to kind of split into two. We have here probability no collision, remember, is what? pt, right? And the probability that there is going to be collision is n sigma v dt. So the two together, probability of this and that, is going to be the product. So this is going to be p of t times n sigma v dt, right? We know what pt is. This is e minus n sigma v t times n sigma v dt. Okay, so one can see this probability to be maybe some probability density f of f star t times dt, right? And you know what f star is from here. You can see f star of t is going to be e minus n sigma v t n sigma v n sigma v, right? Sorry, let me clean this. this is V. So this is going to be useful, we can use it later, and one can see that all such probabilities sum to 1. So this probability, all such probabilities sum to 1. Right, you can see that the integration from minus infinity to infinity dt of f star t is actually equal to 1. Right, so you know what f star t is, you can compute this somehow. If we let's say x to be n sigma vt, and so dx is going to be n sigma v dt, and the integration of dt from minus infinity to infinity e to the minus n sigma vt n sigma v is going to be equal to integration from 0 to infinity x 0 e to the minus x dx, and this is equal to 0 factorial, which is equal to 1. Right? We've used this formula, n factorial is equal to integration from 0 to infinity x to the n e to the minus x dx. Right? So you can see this is a valid probability, so to say. So from that we can now use the probability density function to compute averages. And remember what we want? We want the average time between collisions. So having this probability density is going to solve our problem, because we can use it to compute the average time. Right? We can now use this probability density function to compute averages. In particular, we want mean or average scattering time. Average scattering time, so average time before collision, if we call it tau, mean time between collisions, right? So this is going to be equal to, remember we have used this a lot, we want to compute the average of t, so t times the probability density function dt. We make this integration. I hope you remember this. So you making the substitutions and doing the integration, you're then going to have e to the minus n sigma v vt and sigma v dt. Here we can see this is 1 over n sigma v, integration 0 to infinity n sigma v t e to the minus n sigma v t d n sigma v t. Okay, and this is similar to the formula we have used earlier. Let's say this is 1 over n sigma v, integration 0 to infinity of x e to the minus x dx which is 1 over n sigma v, because the integration is going to be equal to 1 factorial, right, which is equal to 1. Therefore, we have average collision time is 1 over n sigma v. So this is what we need. Now, given tau, the average scattering time, we can now compute the mean free path. Mean free path, we call it lambda. This is going to be equal to the mean speed of molecules times the time without collision, so time between collisions. This is going to be equal to average of speed divided by n sigma v. So this is a formula for the mean free path, right? So lambda is average velocity divided by n sigma v, right? Yeah. We have arrived there, only that if we notice that this v, actually what is it going to be? Is it really the average speed of molecules? The answer is no, because this v is what we have considered using this simplification, that molecule under consideration, molecule A, is moving with a speed v, and like the other molecules in the gas are sitting without any speed, without velocity. Okay? So we're going to correct this simplification as follows. Let's go to next page. Since all molecules in gas are moving, okay, none is stationary, then we should consider v to be actually the average of the relative velocity between molecules, right? So we consider two molecules at a time, and the relative velocity between them is Vr. So where Vr is relative velocity, relative speed between molecules. Okay. For example, looking at it vectorially, Vr can be V1 minus V2, the relative speed between molecule 1 and molecule 2. Okay, and one can consider like Vr squared can be computed to be V1 squared plus V2 squared minus 2 V1 vector dot V2 vector. You can compute this, where V1 is the magnitude of velocity 1 and V2 is the magnitude of velocity 2. Sorry. Okay. And from here, one can compute the average relative velocity squared to be equal to the average velocity 1 plus average velocity 2 squared minus 2 times the average of V1 dot V2. Okay. We know this this is going to be equal to 0 because cos theta, average of cos theta is 0, right? Cos theta is moving from 0 to 1. If you do the average, it's going to be 0. And here theta is like the angle between the velocity of molecule 1 and molecule 2. So if this is velocity of molecule 1, you have velocity of molecule 2. The angle between them is theta. And for computing the dot product, the cos theta is going to find its way, and the average of cos theta is 0. Therefore, we're going to get the average of the relative velocity squared is going to be equal to 2 times the average velocities squared. So v1, average of v1 squared is actually v squared. It doesn't matter which molecule we're considering. So v1's average of v1 squared is equal to average of v2 squared. Average of v1 squared is equal to average of v2 squared, which is equal to the average speed squared of the gas. Okay. And if we assume that we can, it's not totally true, but this is one can do that, like if we assume the average of the average relative velocity to be equal to square root of the average relative velocity squared. Okay, if we assume this, then one can see that we can set the mean free path to be equal to average speed divided by n sigma times average relative velocity, right? And substituting, this is going to be equal to 2 n sigma so it's going to be square root of 2. If we take the square root here, okay, the square root, this is going to be square root of 2 times square root of average velocity squared. So substituting is going to be here square root of average velocity squared, right? Assuming these two can cancel, then this is equal to 1 over square root of 2 n sigma. So the mean free path of gas is 1 divided by square root of 2. All you need to have is the number density and the cross section. Okay, I think that's it. It's enough for today. We're going to stop here. In the next lecture we can expand a bit and talk about sigma more. What does it really mean, the collision cross section? Okay, but yeah, before concluding, one can, let me mention this, that one can use the expression that P is equal to N kBT to have an expression for the mean free path lambda to be kBT divided by square root of 2 P sigma. So if temperature is constant, then we can see that the mean free path is inversely proportional to pressure, or if pressure is constant, we see that the mean free path is directly proportional to the temperature of the gas, and the mean free path is really related to the cross section. Cross section is going to be our next topic, and I think that's it for now. I'm going to say goodbye. See you next time.